Welcome everyone to this week's Autonomy Talks. It is a great pleasure this week to have with us Dr. Angela Fontan, who is a postdoctoral researcher with the Division of Decision and Control Systems at the School of Electrical Engineering and Computer Science at KTH in Stockholm, working with Professor Kalle Johansson. Something about Angela: she received her Bachelor of Science degree in Information Engineering and a Master degree in Automation Engineering in 2016 from the University of Padova. She then moved to Sweden, where she obtained a PhD from Linköping University, working with Professor Claudio Altafini. Her research interests are in the area of network systems and nonlinear dynamics over networks, with main applications to social networks and collective decision-making processes, and also in the area of cyber-physical human systems in the context of smart cities. I think she will touch base on both of those things today in her talk, which is titled Collective Decision-Making on Networked Systems from Social Networks to Smart Homes. And I'm personally very excited to hear more about the subject, and I give you the stage, Angela. Go ahead.
Oh, thank you very much for this introduction. So, yes, as Joelle said, I will touch base on both aspects. And before starting the outline of this talk, I just want to give you the background on why of my research interests and cyber-physical human system. And in particular, I was thinking about that, when we discuss sustainable lifestyle or smart cities, we have that several aspects come into play and which motivate and are also motivated by new societal and research challenges. Or can you see my mouse?
Yes.
Yes, great, perfect. So these aspects include, but are not limited to, we have consumption, we have food, we have mobility, and we have energy use in buildings. And for instance, when we're talking about the building sector, basically in the context of energy policy, the building sector is of particular significance, and the role of this building sector is critical to ensure sustainable development. And in particular, significant emphasis is placed on smart homes or residential buildings, which also serves as basically one of the core talks of this talk. So the aspect here is that the digital transformation of cities allow for a new interpretation of urban systems as cyber-physical human systems, focused on basically well-being and sustainability. And we have an increasing emphasis on the human component and in the interactions with cyber and physical systems. And in one key research challenge in this emerging field of cyber-physical system, human system, is characterizing models of human behavior. In this talk, I will talk about particular human decision-making within interconnected communities, which I will show can be represented as social networks, and also how they adapt during the interactions with smart technologies or cyber-physical systems. And here I'm referring to the roadmap that is going to come out during IFAC 2023 this year. So basically, in this talk, the focus is going to be on collective decision-making on networked system. And the first part of the talk is going to be a bit more what I did in my PhD. So it's more focused on social networks and about finding models of behavior over social networks. While the second part of the talk is more like research directions, new research direction that I'm exploring right now. It's briefer. And in these two different parts of the talk, there are two different applications, one of political decision-making and one of decision-making in smart homes. And again, the first part is going to be a bit more theoretical. So if you see too many technical details, you can just tell me, I can skip a few things. Okay, but let's start with the first part of this talk, and which I entitled, let's say, collective decision-making on the networked system in the presence of antagonistic interactions. And this is part of work that I mostly did when I was a PhD student at Linköping University, as Joelle introduced before. So the problem that we address in this part of the talk is that of a group of agents exchanging opinions and beliefs and information with the objective of reaching a decision. And as many of you know, probably in nature it's possible to find different examples of collective behavior, for instance, in animal groups. And the main common factor between these different examples is that a decision is usually reached through collaboration among the agents. However, this assumption may be too unrealistic when we consider other scenarios, like such as social networks or my example of interest, parliamentary systems, where one can think that it's more realistic to assume that both cooperative but also antagonistic interactions may coexist. So the other problem that we're interested in study is, as I said, now plenty of time is collective decision-making in presence of antagonism. And to do so, we need to consider two different ingredients. One, we need to find a way to model this network or this community where we have antagonistic interactions between the agents. And then let's say the most natural choice is to look at sign networks, where we have that positive edges with a positive weight represent a cooperative or let's say friendly interaction, and edges with a negative weight represents a rival or antagonistic interaction. And then of course we need a model to represent this process of decision making. So for the model of decision making, we have inspired by the works of Naomi Leonard's group at Princeton, and I just want to recap it quickly, and then I will explain how we extend this model to take into account also antagonistic interactions. So basically, this model is made of two parts. We have a diagonal part and we have an off-diagonal part. And in the diagonal part, represented by this matrix delta, represents the, let's say, the inertia of the agents to the development of an opinion, while the off-diagonal part represents the interactions between the agents. We have, in general, a collaborative or cooperative network, showing how basically agent, where basically the weight on the edge represents how the amount of trust between the agents or friendship. And then we have nonlinearities to express how agents, to represent how agents basically express their opinions to their neighbors. And the particular shape of this nonlinearity is sigmoidal. And basically this means that extreme opinions of agents are basically moderated. And finally, we have a scalar parameter, which is a positive scalar, which we call social effort in our analysis. And what has been shown previously is that with this social effort parameter, which we also call strength of commitment, under an assumption on the matrix delta, which in particular is a Laplacian assumption on this Laplace matrix delta, the objective was to study how the qualitative behavior of this model as we vary the social effort parameter. So basically doing what we call a bifurcation analysis of this nonlinear model. So what has been shown is that previously is that basically by increasing the social effort parameter pi, and I will go a bit more in detail later on, but the idea is that the model goes from a neutral state or deadlock, where basically since the equilibrium of the system represents the decision of the community, this deadlock state means that no decision is taken, to basically after this parameter pi increases over a threshold, then this means that the agents reach a right amount of commitment and two decisions are possible for the community. What we wanted to do is to take this model and add antagonistic interactions between the agents. So basically what we did was consider instead a matrix, a sign network, and then study again what is the behavior of this model when we vary again the social effort parameter. So basically first, before introducing how we basically propose this model, we need to introduce some notion of sign networks in case, but yeah, if this is a topic like sign networks is clear to everyone, I can just skip it. But basically the idea is that when we look at the sign networks, it's natural to start by a notion of sign Laplacian of a matrix. And in the literature of sign networks, there are different definitions of sign Laplacian, but the one that we adopt is the following. So at a glance is similar to the usual definition, but the difference is that in the diagonal matrix, we consider we consider that each element I of this matrix delta is defined as the raw sum of the absolute values of the adjacency matrix A of the network. So the difference is that when we consider the Laplacian, and in particular in this talk, we focus on the normalized and Laplacian, where basically the Laplacian is scaled to have basically the identity matrix on the diagonal. The take-home message that I want to give is that basically in this case, for a sign network, the spectrum, all the eigenvalues of this Laplacian are non-negative by choosing the absolute value. This is due to choosing the absolute value in the matrix delta. And the second notion that I want to introduce when talking about sign networks is that of structural balance. And we say that a network is structurally balanced if it's possible to basically group or divide or partition the agents into two groups of mutual friends. So in this case, we have all the nodes in V1 are friends with each other, and all the nodes in V2 are friends with each other, where there exist only negative interactions between the two groups. And it's called structurally unbalanced otherwise. So basically a structurally balanced versus a structurally unbalanced network in the social context represents situations where basically there is no tension or less tension among the agents. So let's consider an example to go a little bit away from the theory. So in parliamentary systems, basically where the parties have to negotiate with each other in order to reach a coalition, a possible coalition that needs to receive basically the support of the whole parliament, or at least of the majority of the parliament, then we can think that a two-party parliament can be presented as a structurally balanced network, where we have party 1 and party 2, while a structurally unbalanced network is better represented by a multi-party parliament, where basically we can think that all this tension and rivalries between different political parties is what makes the network structurally unbalanced. Okay, so analytically, it's possible to give different definitions of a structural balanced network, basically which apply for networks that have more than 3 nodes. And I will first read it and try to explain the example. So, for example, the first condition means that applying special transformations, which are called, for example, signature similarity transformations, then we obtain a graph with only positive edges. So basically, this means that the signature similarity transformation of the normalized and Laplacian as all non-positive of diagonal entries. The conditions that for me is the most important in this talk is that the smallest eigenvalue of the normalized and Laplacian is 0, which also means that if we consider a network is structurally unbalanced, if the smallest eigenvalue of the normalized and Laplacian is strictly positive. So one can see the structural balance versus structurally unbalanced as a condition between positive semi-definiteness and positive definiteness of the Laplacian matrix of the network. Okay, so now that we have defined what we mean by structural balanced network, so a network with less tension between the nodes, then it's natural to ask, okay, but how far is a network from a structurally balanced state? And the standard measure is the it's the frustration index, which I will call frustration for simplicity in the rest of the talk, which is basically the minimum overall possible signature similarity transformation. So basically this transformation that I introduced the definition earlier of a certain energy functional. Now the formulation does not matter now. What I would like you to grasp, or to, what is the message that I would like to bring, is that the computation of this frustration is an NP-art problem. So it's not, while it's how we define this distance, then it's difficult, right, to compute. So what other measures in the literature that have been considered is the algebraic conflict, so the smallest eigenvalue of the Laplacian, which we know to be positive for structurally unbalanced networks. And by simulating, by numerical simulations, one can see that this algebraic conflict or smallest eigenvalue of the Laplacian is a good approximation of the frustration. And this is basically the end of the more like theoretical part on sign networks, this idea that there is this frustration of the network, identifying some type of social tension in the network, and that this frustration can be approximated by the smallest eigenvalue of the Laplacian of the network. Okay, now we have all the elements that we need from sign networks, and we can define our model. So basically we take the same model as before, so a model with a linear and a nonlinear part with sigmoidal nonlinearities. But now what happens is that the adjacency matrix of the network is a sign matrix, or is let's say the network describing the community of agents is a sign network, where basically now what is happening is that each element of the matrix A, the sign represents the type of relationship, so cooperative or antagonistic, while the absolute value represents the amount of trust or distrust between two agents. So now we have the model, and it is, again, we make special assumptions on this model in order to be able also to study this model, which is again a sign Laplacian assumption, and which permits us to give an expression of the Jacobian of this model with respect to the normalized sign Laplacian. And this is a little bit the idea here is that then since we can think about the Jacobian in terms of the sign Laplacian matrix of the network, then we have that we can express a relationship between the monotonicity of the system and the structural balance of the network, and then the smallest eigenvalue of the normalized sign Laplacian. I put a slide in case there are people interested in monotonicity versus non-monotone. So the idea is that the system, this model is going to be monotone if only if the network is structurally balanced. And the task was to investigate again how the social effort parameter pi represents the existence and stability, affects the existence and stability of the equilibria, and then also to study what happens when we add these antagonistic interactions in the qualitative behavior of the system. And we have different tools. They come from bifurcation theory and sign network theory. So basically this concept of frustration that we have used, that I've introduced before. Okay, so what we did was a bifurcation analysis, and I will explain it first in the structural balance case, and then in the, let's say, more complicated structurally unbalanced case. So in the right, we have a bifurcation diagram. So we can see how the equilibria, basically this depicts how the equilibria of the system, in this case for two nodes I and J, changes as we change the social effort parameter. So again, as before, we have that when the social effort is small, the system admits only one equilibrium point, so the trivial one, the origin. And we all can also establish the stability, so the global asymptotic stability of this point. And this point is represented by this black branch. And then as soon as the parameter pi increases and crosses 1, a pitchfork bifurcation appears and two new equilibria, that's represented by these red branches, appear for the system. But then by increasing even more, by further increasing this parameter pi, we have a second branch and we have a second pitchfork bifurcation, and then multiple equilibria, which can be stable or unstable, can arise for the system. And what we have found out is that, okay, but this was the structurally balanced case. Then we wanted to analyze what happened in the structurally unbalanced case. And the interesting thing is that by just redefining these threshold values, pi1 and pi2, the behavior was exactly the same. So we redefined this value pi1 and pi2, and again, we see a first pitchfork bifurcation and then a second pitchfork bifurcation. So basically, this means that the qualitative behavior of the system was exactly the same. And I was I was thinking, let's just skip the proof because I would like to show you something else. But the main idea why I wanted to put the sketch of the proof, and I can just skip it, is that in the structurally unbalanced case, since the system is non-monotone, we cannot really use the standard tools that we use for, for cooperative or nice, let's say, systems. So, for example, again, we can still use Lyapunov theory to show that there is the sufficiency for a first pitchfork bifurcation, but then it's not a standard quadratic Lyapunov function, for instance. While then we need to resolve to, to singularity theory and to basically bifurcation theory to show that there is a pitchfork bifurcation for each threshold values, which basically, this is a fancy term to say that we need to map our system in the center manifold and then find out if the derivatives of this in the center manifold satisfy some special conditions. At the end, this was just to say that one has to think a little bit more creative when one goes from monotones or nice systems to like no monotone or structurally unbalanced systems. Okay, so now we have shown that the qualitative behavior of the system, and now I want to give an interpretation of this system in terms of this parameter pi, our social effort, and in terms of the frustration. So let's start with the social effort. And in this figure, basically, I plot the smallest eigenvalue of the Laplacians, so lambda 1 and lambda 2, and how they change with the increase in values of pi. So when we have that pi small, when we have a small effort among the agents, again, we have no decision, so a deadlock situation. Then when we increase the commitment among the agents, if we cross a level of right commitment, then we can obtain two alternative decisions. And then finally, when the social effort becomes very large, then we are in a situation of overcommitment, and then several decisions for the agents or for the community are possible. Okay, so the first one was the interpretation in the social context, and now we want to understand the second task was, okay, but how the antagonistic interaction actually affect the behavior of the system. So basically, what happens? Does these threshold values, how do they depend from the frustration of the system? So the first threshold values, the interesting thing is when in the structurally balanced case is always fixed, equal to 1. But then the nice thing is that since we know that the frustration can be approximated by the smallest eigenvalue of the normalized Laplacian, we have that for structurally unbalanced graph, this value pi1 increases basically with the frustration of the network, which is represented by this symbol. While instead, pi2 can be shown numerically that is independent from the frustration of the network, meaning that this gap between pi2 and pi1 decreases when the frustration of the network, when we consider networks with higher frustration. So the take-home message of the, let's say, now the theoretical part of the talk is finished. And so I promise, I think we might have another equation later on, but yes, the theoretical part is very finished. So what are the take-home message I want to bring you from this theoretical part before we go to the application? We have the social effort of the agents grows basically with the frustration or the social with the frustration or the social tension in a graph. So basically this means that the higher is the frustration in a network, the higher has to be the social effort from the agents needed to achieve a non-trivial decision. So to actually achieve a decision between the agents. And then also a byproduct is that basically the higher is this frustration, the smallest is the interval for which basically we know the behavior of the system, for which we have only two alternative decisions. Because after this threshold pi2, the behavior of the system becomes multiple equilibria can arise, and it's very complicated to understand what is happening in this. We actually don't know what is happening in the system. Okay, so we want now to use these results, so this idea of frustration, to basically to consider a concrete application, which is on political decision making. And in particular, we decided to look at the government formation process in parliamentary systems. So if you're not familiar, in the government formation process starts with the legislative election, after which basically each political party receives a certain number of seats in the parliament, depending on the number of votes gained at the election. And then if no party or coalition has managed to secure the majority of these votes, then a negotiation starts between these political parties. And then the outcome of this negotiation is basically a coalition, a cabinet coalition, which receives the support of the parliament through a vote of confidence. And what we found out, or if you actually are interested in politics, is that this government negotiation phase might be a complex and very long process. And in particular, in the past decade, we have seen an increase in the duration of these government negotiations, defined as the number of days between the day of the election and the day the cabinet is sworn in. And this has happened not only in countries that are famous for this type of behavior, such as Belgium, which I think holds the record with 541 days of government negotiations, but also in countries such as Italy, such as Germany, or even Sweden. Since I am in Sweden, basically the election of 2018 from Sweden is what actually motivated or inspired this more like application. And what we asked was if we can use our model for decision-making over antagonistic networks to explain this behavior. So the idea is that we can think of this process as a collective decision-making process in which the parliamentary members, so our agents, need to cast a vote of confidence, which is the decision, to a candidate cabinet coalition. So the idea is that we can map the parliament into a sign network. And then if we measure the frustration of this parliamentary network, then the intuition is that the duration of negotiations should increase with the frustration of the network, meaning that the higher the frustration, the longer I expect the negotiation time to be. So, okay, to evaluate this hypothesis, we considered the legislative elections in 29 European countries from in the last roughly 40 years, where the analysis stops at 2020. And we calculated the Pearson's correlation index between the frustration of the parliamentary networks for each election year and the duration of these government negotiations. So here we have an example of the German elections. So we collected the number of days, the frustration, and then we computed the linear regression or Pearson's correlation index between the duration of the government negotiations and the frustration for each election date. Okay, But first, we needed to understand how to construct these parliamentary networks. And so basically we map, as I said before, we map the parliament into a parliamentary network, and we make the assumption, which is standard in this literature, but it's that basically parliamentary members that belong to the same party actually vote in line with their party. And we make this assumption because we consider, government formation processes that should happen just after the election, where we can assume that there is this party loyalty is still high between the parliamentary members and their party. So due to this assumption, we can basically gather parliamentary members from parliamentary members in the same party, in a big party node. And then we can build basically a big parliamentary network as follows, where we assume that there is collaboration between parliamentary members belonging to the same party. And then there is rivalry or antagonism between parliamentary members belonging to different parties. And these, let's say, big party nodes can also be represented as a block where unweighted adjacency matrix, in this case, in the first case we consider, where again we have that diagonal blocks are collaborative and the off-diagonal blocks are antagonistic. And then, now that we have defined the parliamentary networks, we wanted to check if the actual parliamentary networks in all these 29 European countries have zero or no zero frustration. And since I'm Italian, originally, I decided the next example will be with Italy, which is actually quite a nice example of parliamentary elections. So we have, for example, that yes, if we consider the parliamentary elections for each election year in Italy, we can see that the frustration is definitely not zero. It's, closer to 200 in this case. And then when we look at all the networks and all the data points basically considered in all the countries, we can definitely see that, yeah, the frustration is non-zero. So networks are indeed structurally unbalanced. So basically there is always some tension between the political parties, which is what we were expecting. Okay, so then we computed this, the correlation between the duration of the government negotiations and the frustration of the parliamentary networks. And these are the results. So we obtain an average correlation of 0.42 for all the, all the 29 countries we consider. And the interesting fact, I will not go that into this talk now because I don't have the time, but even for points that have a negative correlation, we actually found a good explanation for the reason why we have a negative correlation. And of course, but yeah, we were quite happy because just for a simple model was rational is basically this collective decision-making model, we obtained quite a good value of correlation. And of course, this model can be extended, considering, for example, coalitions and ideological differences between parties. So, for instance, one can think that if there is a pre-electoral coalitions, then parliamentary members in pre-electoral coalitions are collaborating, or one can also think about, representing parliamentary members or parties on left-right scale. So, to achieve weighted adjacency metrics, where their position in a left-right scale, there are like databases online. For example, there is this relay number, which gives position of each party in a left-right scale, depending on their political manifestos of the parties. So of course, the more information that we can always increase the amount of information that we can capture in the network, in this sign network. And when we did that, and again, I want to consider the example of Italy because I think it's very interesting. So when we did that, for example, for Italy, the correlation went from a very low number, like almost zero, to 0.45 to 0.95. And here the idea is that, if in Italy is very common to do pre-electoral coalitions, much more than other European countries, which will explain why including also this information in the network improves the correlation. And there is also a big difference in the left-right scale between political parties. which also explain this increase in the correlation. And yeah, here I have the results among the whole, all the 29 European countries. But again, I think that this example of Italy represents quite well the type of the work, let's say. Okay, so the conclusive remarks on this first part of the talk, and I know I'm a bit late, but what I wanted to show you here is that, you know, we are thinking about collective decision-making and understanding. And in this part of the first talk, I gave an example on how by using this, using the rationale or the some type of explanation given by our model for collective decision-making over sign networks, we can use this information and apply to processes of political decision, to an example of political decision-making. And where in particular we were looking at how the social effort among agents can be interpreted as a function of the frustration or the amount of disorder or tension in the sign networks. Okay, so this concludes basically the big part of this talk, and this is what I did during my PhD studies. And as Joelle said before, I'm still definitely interested in human decision-making and social networks, but now I'm switching slightly the application, and I'm more interested also in thinking about human decision-making and how humans interact with smart technology and these complex interactions between, and how basically this interaction affects this modeling of decision-making. And yeah, these are just some of the collaborators that I have, in particular Masa, that is a student I'm collaborating with. Okay, so the motivating example for the second part of this talk is, in this case, we consider collaborative agents, but basically the second example of this work is the design of approaches to improve building energy efficiency and energy performance. So how can we do that? And in this context, basically, it has been observed that aside from practical issues that are commonly encountered with working with real data in buildings, a major challenge lies in understanding the complex dynamics of occupants, encompassing their interactions with the residential building, but also with other tenants themselves. So, for instance, influence of occupants' behavior can be observed in the gap between estimated and measured building energy performance, due, for instance, to unexpected behavioral patterns of occupants. And I have multiple examples. For instance, in our case, we have occupants that, for example, leave the windows open during winter times, but at the same time open the radiator. So like electrical radiator, which these are the type of behavioral patterns that we cannot really think about when we try to estimate building energy performance. And then the second is that is the difference between the gap between surveyed and observed opinions or behaviors of occupants. And this is due, for example, to a desire to seek social approval. And again, this example is consistent with representing this new urban system of smart homes as a cyber-physical human systems. And in the challenging task of trying to improve our understanding of human decision-making, we are looking at different research directions. I just want to mention one, which is the first one, which I did not manage to fit into this talk. So the first direction that we are looking at is to look at, for example, the drivers, the environmental drivers that are making occupants interacting with windows. So this is just an illustrative examples. And if you are going to go at the IEEE CCTA, the conference in August, then Masa, the student collaborating with, is going to present these results. And in particular, but what is my particular interest in is trying to understand if sustainable behaviors can diffuse within social groups, or how sustainable behaviors can diffuse within social groups, which is what I will present also at IFAC. So what we did was to do a longitudinal experimental study. We go away from the theory, and now we are doing an experimental study of social influence in behavioral changes towards sustainability in the context of smart residential buildings. And basically, there are diverse strategies that want to investigate and motivate behavioral change in smart homes. And this diverse strategy has been explored in the literature, but basically the concept that we introduce in this work combine these factors and wants to propose a new social network perspective when we frame the experimental design as a collective or household decision-making process with interconnected tenants living in a live-in laboratory as the decision-making. Okay, so, and basically the implementation of this experimental study relies on both qualitative data, so data collected from surveys from participants, but also on quantitative data, so sensor measurements coming from a live-in lab. So the approach consisted in observing to define a sustainability score for each tenant, and I will define that later. That's the last equation I have, and observe how the sustainability score changes over time. And we want to examine two different sources of social influence. So we are interested in observing whether by discussing with neighbors, their sustainability score changes, or whether by observing neighbors' behavior or the average household sustainability score, the sustainability score of each tenant change. But the key point is that digitalization of smart homes basically allows not only for virtual communication between the occupants, but also for interaction with the building. And as basically I introduced in the previous slide, this experimental campaign wants to propose and is inspired and could be explained in terms of theoretical dynamical networked model for collective decision-making, where basically the social network, a smart home can be mapped into a social network of interacting tenants, which are connected. They can be, in this case, they were connected physically, but they were also connected for now. And then we have the decisions of the lifestyle choices that these tenants make. And of course, there are different challenges in an experimental design. Something that some of the two most important challenges, for example, is to define what we mean by behaviors, to derive the sustainability score, and then identify how we measure behaviors of tenants. Okay, so before approaching those challenges, I just want to talk a little bit about the experimental setup we have on. So the campaign was run at this KTH Live-in Lab. So at KTH, we have the very nice opportunity. There is a state-of-the-art platform of building testbeds. And thanks to this platform can be seen as CPHS. So we have a data pool with an extended sensor network, so the Cyberport. We have the customizable layout, so the walls inside the walls can be moved so that one can have, in this case, the layout that we have private apartments, but also shared spaces where the participants actually live full time and, interact with each other. And then we have also interaction capability with and between occupants. So we can see the KTH Live-in Lab as a full cyber-physical human system. So this is the design of the case study, and in particular, what I'm going to describe now is what we call the preparatory phase of the project. Was data we are still analyzing. So even if the campaign is finished, we are still in the process of finishing to collecting the sensor data. And this campaign included only 5 occupants and a short time period. And after this preparatory phase, we plan in the future to extend this work to an execution phase with with a large group of participants. So it started at week 0, where basically, thanks to surveys, we obtain a reference state on the sustainability, let's say, measure for each occupant, which we classify between 0, not sustainable at all, to 100%. And then at each week, basically, again, at the end of each week, we ask the tenants to compile a survey from which we can calculate the sustainability score, from which we can calculate the average household sustainability score. And using this information, we give this information as feedback to the tenants at the beginning of the next week. So what is happening is that then at the beginning of the next week, the tenants can decide to act on this information or continue to behave according to their habits. And then we repeated this example, this procedure for the whole 5 weeks of study. So measurements, feedback, etc. And now we are basically in this phase where we are still trying to finish the data analysis, and we are trying to gather feedback from tenants that are at the moment under exams. And I just want to stress that, again, we have 2 sources of social influence. The first source is communication among tenants. They live together and they talk to each other. We actually ask them to discuss the content of the surveys, etc. But this data we cannot measure. We can only measure at the beginning and then the end of the week. And then we have some type of observation. So that is due to the feedback that we give to the tenants at the beginning of each week. Okay. It's finally time to describe the sustainability scores before showing you the preliminary results. And I promise I almost finished the talk. So when defining the sustainability scores, the important thing was to understand what we mean by environmentally significant behaviors. And by looking at the literature, we define activities for which a correlation between environmental impact and behavior is established. Drawing basically a 17 questions questionnaire or a survey, which spans, let's say, 5 lifestyle behaviors, from resources to consumption to food, mobility, and environmental citizenship. So we give this survey to the participants, and then we compute. At the end of each week, we can look at the surveys, and then for each tenant, we can compute basically the past week actions, which are represented in this case by a state variable y, where q is the number of activities. In this case, we are considering 17 different activities. And then we can calculate, based on this data, the sustainability score for each tenant, and then also the average household sustainability score, basically looking at the average among the scores of each tenant. And these are the preliminary results. Again, it's a small sample, so we cannot really conclude any big results in terms of statistics, but what we see is that in black, we have the average household sustainability score. And the interesting thing is that, for example, we looked at this tenant, the purple one, increased definitely their sustainability score. So that was, these are like observations that we are making now, and now we are waiting to obtain the sensor data from this Live-in lab to compare the data from the surveys to the data obtained due to actual sensor measurements. And basically, to move from this preparatory to execution phase, and we have the opportunity to use 305 apartments. Of course, we would like to evaluate if the social influence between the tenants is enough. So this feeling of social connectedness is strong enough between the tenants. And then we want to use this data to evaluate models for collective decision making. And we want to also evaluate the awareness of tenants regarding their behavior by, as I said before, comparing this data from these surveys to data from sensors collected at the KTH Live-in Lab. Okay, so this was basically my last slide. So what I did, this was a big talk, and I hope I did not go too fast, but basically the interpretation or the background, the context of this talk was thinking about urban systems as cyber-physical human systems with all the challenges that come with this, within this emerging field. And the focus in particular was on human decision-making within interconnected communities. And then we looked at more like when we have interconnected, more like at a model in antagonistic interactions, and then interconnected communities and their interactions with the building. And I think I brought two concrete examples, one on political decision-making and one of decision-making in smart homes. And I very much would like to thank you for the attention and for inviting me to give a talk today. And I would be very glad if you have comments or if you want to discuss offline with me. Yes.
Thank you, Angela, for the great talk. Very interesting stuff. Let's open the stage for questions. You can either raise your hand and directly ask or write in the chat and I will read for you.
Okay, Joel, if I may break the ice.
Go ahead, Emilio.
Angela, yeah, thank you very much. This is very, very interesting.
Thank you.
Now, you know, especially like I was actually surprised that there are other countries that have a worse political system than ours, than Italy.
I don't want to say worse, you know, this is like, but yeah.
It takes longer. Okay.
Yes, exactly.
Now, the engineer in me, you know, can't help but wondering, okay, so, you know, clearly there are some things that are broken. How do we fix them? So,
in which context? Sorry.
So in the frustration thing, right? So okay, so you had this measure, this frustration that shows that, especially when you introduce coalitions and things like that, that seem to align well with the time that is necessary to actually form a government. Now, is there any way that you can think of some mechanisms that could reduce that frustration?
Oh. That's a good question.
That's the engineer in me, right? So this is a nice analysis, right? But I can help but thinking, okay, how do we fix this, right? So
no, sure, that is a good point, because I think let's say, I don't want to say problem, but the thing here is that by looking, basically, the parliamentary networks are a snapshot of the elections, right? So the frustration represents the election day, and that can give you an expected number of days or unexpected length or duration of the government negotiation process. And also we show in the paper that it gives you an idea on how the coalition of the government is expected to be, which I did not present here due to time constraints. So one thing is that it actually gives you, I know, please, don't take me too formally, but it gives you an idea on what the candidate, a good candidate cabinet coalition with the less social tension should be. So in one way, if you know, could suggest what a candidate cabinet coalition could be in terms of less tension, that could, but again, I'm not sure about how to solve like a feedback of this type of work.
I was thinking of, you know, what if there is a requirement for a commitment to something, right? So before the election, right?
You
know,
I mean, yeah, one could, but the problem is that you need to know, I mean, first you need to have an idea, because there is a threshold normally on the parties that, what is it, the 4%, they need to receive a certain amount of votes in order to be allowed to be in the parliament, which is something that one can think, which is something that we cannot know 100% sure before the election. We can, you know, imagine which parties. So the construction of the network must happen the day of the election. So in that case, sure, one can think about the possible different coalitions or pre-electoral coalitions that one could make in order to decrease the frustration of the network. But I think it's going to be difficult to implement. Like, it was going to be difficult to go to a party and say, you know, if you make this coalition with this party, we'll have a better chance. Or, you know, during the negotiation period, if you make candidate cabinet coalitions with these other two parties, then you will reduce the process and you will have less social tension. I think going to the actual human, this was an interesting work in the sense that by just looking at the snapshot of the elections, we could expect, you know, the length. So it was some type of, let me use this term, causality between the frustration and the length of the period. But I don't know, it's an interesting question. I would like to, yeah, I did not consider that. But yeah, it would be nice to see how that would apply in Italy.
Yeah.
But since you were talking about Italy, in Italy there is also not the problem, but there is not maybe, I think it was more in the period of time that I was considering where we have this, you know, the 5-star movement that is a big tent party. So indeed, this model, for example, when we include the left-right scale, they don't really, big tent parties don't really fit into a left-right scale. So one could make models a bit more complicated by considering different factors but yeah, there are all these factors that appear in real life, like big tent parties that are very difficult to capture in this type of models. That's why we were so happy when we saw that was still quite good correlation. But yeah, Italy is definitely one of the examples that we were looking at.
Okay. Yeah, thank you. Thank you very much.
No, thank you.
Very thoughtful.
I'm happy to have some Italians here in the chat. I was counting on that.
Any other question, Angela? I actually have one which is a bit connected to what Emilio asked, which is maybe not about designing a different system, but it's, have you thought about, so right now this analysis tries to explain some behaviors with your model, and it seems that the model captures the behaviors pretty well.
Yeah.
So the next question for me would be, what happens if single parties start using this model to influence the system? Have you thought about that?
No, the quick answer is no. One thing is that, for example, we did not, there are, from a theoretical point of view, I know that Naomi has looked at what happens when we use in this parameter, the social effort or bifurcation parameters, when that parameter has some type of feedback with the state. So where there is control in that parameter, we did not analyze that. She did that for cooperative systems, but no, we did not take that into account. So if parties, like the way that parties could use this information is, you know, to think about what is a potentially good candidate cabinet coalition with the less tension, thinking that if a candidate cabinet coalition has less tension, maybe the government will actually last a bit longer. And I was thinking about Italy, but this is like all like, it's not something that we consider. This is like things I intuitive things that I'm thinking about, because for example, in Italy, in the last 75 years, we had 65 governments.
Exactly, like it's the opposite of lasting longer.
So maybe if they would have made the candidate cabinet coalition reducing the social tension, then no. But yeah, that could be a way, but I will not be able to answer fully. If you have ideas, they are very welcome.
Oh no, it's just, again, I'm not an expert of these things, but I see a model, I see it works, and then I think about how people might leverage it for the good or for the bad. Like it's
that is definitely something interesting. I had the ambition of keeping on collecting this data and keep this database, because right now I have this database until 2021. It would be nice to keep it updated, but sadly I've not had the time yet. But I would like to see if, you know, this model keeps on working. It just takes a bit of time to collect all the data, actually. Yeah. Very,
very cool stuff. Wait, there is a question in the chat. Yes. So let me see. Shima is asking, thank you for the interesting talk. I wonder if we can also define and consider more types of interactions in networks rather than only two extreme types of collaborative and antagonistic interactions that are simply represented by plus and minus.
Question, do you mean weighted or +1, -1, or I'm not sure what other type of interactions, because right now, if we think, let's pick this example. Okay, it's a bit complicated, but right now we are only thinking about, you know, about, actually, let's pick an easier figure.
It's like a two-dimensional, it's a two-dimensional set, right?
Yeah, it's a two-dimensional, and I consider symmetrizable or basically undirected graphs. Of course, it becomes much more complicated when one considers directed graphs, and there are no multiple edges. So I have no idea what will happen in that case. Like when we have directed graphs, I know that one can have other type of behaviors in the model, for instance. Yeah, we only consider weighted negative or weighted positive. I'm not sure what other type one could. Okay, yes, sorry. Maybe I can say something more. One thing that we were thinking at the beginning is that I saw in certain articles on political decision making was considering different informations captured by edges. So some type of multi-layer network for each edge representing a different different dimensions on political beliefs, but we just consider a two-dimensional networks, because I have actually no idea how to extend the theoretical model to include more complex graphs, honestly. But that would be interesting. I just don't know how to do that. Yes.
Thank you, Shima. If you have a follow-up questions, just type it.
I hope I answered.
Yeah, I see in the chat is still the old question. So
yeah, exactly.
Any other question for Angela? If not, I guess in one of your slides you had your email in case people want to reach out.
Yes, please do. Or check me out. I've put at the end. And I think you had it too. I have my personal page that I try to keep as updated as possible. And well, if you let me say, just if you don't mind, I was talking about before about the roadmap. The IEEE CSS roadmap is now available, publicly available. If in particular, I'm interested in cyber-physical human systems, but one can look at different. It's like a roadmap for the future and control and societal challenges where the control discipline can help. So if you're interested in, please check it out, because now it's out. So yeah, that's it. Just a bit of commercial.
Summer reading.
Yes, exactly, a summer reading. Yeah, during IFAC or during yeah, sure.
Very nice. Thank you again, Angela, for the great talk. It was a pleasure, and good luck for the next steps.
Yes.
And thank you all for participating, and see you all next week for the next Autonomy Talk. Bye-bye.
Thank you so much. Bye.